So I'd also like to thank Richie. I think Richie and I spoke, I don't know, it was probably a year and a half, 2 years ago. We spoke about using GFRP in slabs-on-grade, and he had a lot of really great questions, and I didn't have a lot of really good answers at the time. So one of the things that we talked about, though, is that here at ACI, we have a lot of people who are expert in GFRP, and we have a lot of people who are expert in slabs-on-ground, but we're really not talking to each other. And so really, I think a lot of that is the impetus for what we're doing here today. We want to put everybody in the same room. We want to have a little bit of a discussion on what are the things we have to think about with GFRP, and then what are the things we have to think about with slabs-on-grade, so that we can all start to come to some collective understanding of how we can do these things appropriately out in the field. So that's really what I want to kind of talk about today. I want to talk a little bit about GFRP reinforcement at kind of the basic level. For those of you who know a lot about GFRP, I apologize for getting too far down in the weeds on that. And then I want to talk a little bit about using this material specifically for slabs-on-ground, and a little bit about the development of this particular document. So this document, if you're not aware, there are a couple of documents that are co-published by NEX and ACI. And I think this is really kind of the power of what NEX brings to the table. When we have industry needs, when we have a lot of questions about particular topics related to the use of nonmetallics, NEX is able to help put resources together to help develop these types of documents and drive this type of thing forward in the industry. So this particular document was driven out of a need from the GFRP side of having what we call a pre-engineered manual for using GFRP. So these are using GFRP in applications that are not your high-end engineered applications. These are applications in the residential market, looking at things like foundation walls, and the residential and light commercial application of using GFRP in slabs-on-ground. And can we give some basic guidance to average contractor out there using this material in terms of how much reinforcement they need to add? So, so we started developing this manual, and when we turned to the slab-on-ground question of how much GFRP reinforcement you need to use in these slabs-on-ground, there are a lot of things we had to start thinking about, and that's what I want to kind of show you what we looked at and what we started considering when developing this particular manual. But bear in mind, these are not the really sexy applications of slabs-on-ground, if there is a sexy application of slabs-on-ground, I don't know. These are not Amazon warehouses. These are not heavy industrial slabs. We're talking about residential, light commercial types of applications. So very simple, basic slabs-on-ground. But I think it at least starts to kind of spark in your mind some of the things that we have to think about when using GFRP for other applications as well. So when we think about GFRP, I give a lot of talks about how we design GFRP reinforced concrete, and there's a lot of things that we talk about. There's a lot of things you have to understand about GFRP and the difference between GFRP and steel that really become important when we start talking about designing GFRP reinforced concrete. We've mentioned a lot of these already. We all know that GFRP is corrosion resistant, and that you don't have corrosion issues with GFRP, and that's one of the major reasons for using it. But really, when we're talking about using it in these sort of lower-end residential types of applications, really the primary impetus is that it's easier and cheaper. The reinforcement's very lightweight. It's easy to handle on the job site. It's easy to cut. It cuts like cutting through a piece of wood, not cutting through a piece of steel. So they're easy to cut, easy to place, and they increase productivity. So there's a lot of the benefits more on just the application side that have led to the use of GFRP in a lot of these applications, and particularly in slabs-on-ground, using this starts to make a lot of sense from the contractor's perspective. But from an engineering perspective, we do have to understand that there are a lot of advantages to using GFRP, but there's also a lot of differences between GFRP and steel. So that's kind of the things here on the right-hand side of the screen. Tony mentioned, the reinforcement doesn't yield. It's a linearly elastic material. It's also, though, a low modulus material, which becomes important when we start talking about slabs. Of course, we understand that because it's non-ductile, you can't field bend the material, so you're not going to be bending it into hooks and that type of thing. That can be done, but those have to be done by the manufacturer of the bar, not out in the field. But I think from a slab-on-ground perspective, there's really a couple of key things to keep in mind relative to the material itself. The first one being that these materials are higher strength than steel. So, if you think about typical steel reinforcement being 60 KSI, GFRP is generally 100 plus, so almost twice as strong as regular reinforcing steel. But it is significantly less stiff than steel. So doesn't have the same modulus as steel, is quite a bit more flexible than steel, and you can see that in the stress strain diagram there. The blue line being GFRP, a lot less stiff than steel, which is the red line. The other thing to keep in mind is that these materials are anisotropic, so they have different properties depending on which direction you're looking at. So GFRP would have strength in the long direction, but would have lower strength in the perpendicular direction. Strength is one property. There are other properties that we have to think about as well. We can talk about the shear strength of these materials, but really a lot of mechanical properties change depending on which direction you're looking at with the bar. So that has some implications that we have to think about as well. And I'll talk about those. So when we look at just the structural performance of GFRP reinforced concrete, I think it's important to think about how we approach GFRP reinforced concrete from an engineering perspective. So what you see there is just a typical FRP reinforced concrete beam, or just a reinforced concrete beam. And we're approaching the design of that beam with steel, and we're approaching the design of that beam with GFRP. So the black line that you see here is the design with steel, and the blue and kind of magenta line is the design with GFRP. Those designs are all targeting the same moment capacity, which is the green line. So they're targeting the same moment capacity, but the behavior is quite a bit different, right? So obviously the GFRP reinforcement is designed to be stronger because it is non-ductile. We want to have a higher safety factor. So the GFRP beam is designed to be stronger, but really the strength of the GFRP beam is really almost irrelevant because of serviceability issues. So the real distinct difference between the performance, in my mind, is that you're getting a lot more deflection and a lot more cracking of the GFRP beam than you are the steel beam in the elastic range. So although strength is important and we like strength design, when you're designing GFRP, really the major performance difference is on the serviceability side. So you're trying to design a beam with reinforcement that's much less stiff, so you're getting a lot more deflection, a lot more cracking. So that's really what's going to be driving a lot of the design considerations. And I think it's important to point out that when we look at the design of GFRP reinforcement, and we look at things like the development of the new ACI code, which is the 440.11 code, we're not accepting the fact that GFRP has higher deflection and higher cracking. What we want to do is we want to match the performance of regular steel reinforced concrete. We're not saying that it's okay that GFRP cracks more or deflects more. We're saying we want to match the performance between the GFRP reinforced element and the steel reinforced element. So the philosophy of a lot of the design equations that are in the 440.11 code are really geared around designing the serviceability of that member to match what the steel reinforced concrete beam would do. So we're not accepting, the fact that we get more deflection and cracking out of the FRP. So now when we start talking about using GFRP to reinforce slabs on grade, in my mind, we have to take the same approach. We want to have similar performance to what we expect with a well-designed slab-on-ground type of application. So when we started looking at the development of the manual for this residential application, that's really what we started thinking about, is how do we match the performance of what we expect with a steel reinforced slab on ground. So again, what I'm going to present now is just kind of the background for what's in this simple little manual, but bear in mind again that we're trying to match performance of what we know well, which is steel reinforced slabs on ground. Okay, so when we started looking at this, there were a couple of approaches that were out there. So a lot of people have talked about this document. This is ACI 440.1. This is not to be confused with 440.11. 440.1 is the original guideline document for GFRP reinforced concrete. And this document actually had an appendix for slab on grade design using GFRP. So there's been a lot of questions about this document, and I think rightfully so. So this document in the appendix talks about using a method involving subgrade drag. Does everybody know what subgrade drag is? The slab on ground guys do. So subgrade drag was a method of approaching a slab on ground that was used, I guess, historically, but that method was dropped from ACI 360, I think, back in 2006, because of a lot of concerns with the way that that equation actually played out, led to some problematic issues, and a lot of this was due to the fact that maybe it was underestimating some of the shrinkage crack, some of the stresses that were going on. But this equation has been largely dropped again by the slab on ground community, I would say. But it is still in this document in 2015. So that's again where I think, the GFRP people and the slab on ground people need to have more communication, because really this subgrade drag approach that's in that document is really outdated, and we need to look at other methods that are out there currently. So, so this was one approach, but this was an approach that we quickly abandoned just because it didn't seem to make much sense in the industry currently. The other approach is just to use minimum reinforcement, right? So ACI 318 has requirements for minimum reinforcement in concrete elements for temperature and shrinkage. You could just use those minimum reinforcement requirements, adjust them for FRP. And that's what 440.11 generally does. It takes the requirements from 318 for minimum steel for shrinkage and temperature, makes some adjustments based on the material properties of GFRP, and presents a new minimum reinforcement for GFRP reinforced concrete. However, when we're looking at slabs on ground, use of minimum reinforcement is also problematic. You actually end up, in many cases, over-reinforcing the slab. So the issue becomes that if you have minimum reinforcement in the slab, you start essentially locking up the contraction joints, and cracks don't necessarily form where you want them to at contraction joints. They form at other locations in the slab. So that approach for slab on ground isn't really applicable either. So if we look at 360, 360 has a number of different approaches, but again, bear in mind, we're just thinking about low-end sort of residential applications at this point. So 360 has an approach called enhanced aggregate interlock. I think James kind of alluded to this at the very beginning. And this approach is where you use a very small percentage of reinforcing steel for shrinkage and temperature. And the contraction joints really control where the shrinkage cracks occur. The reinforcement, though, does not lock up that contraction joint. It allows that contraction joint to stay active and to crack as we want it to. So if we look at our contraction joint, whoops, missing a graphic there, but if we look at a typical contraction joint, we have reinforcing crossing the contraction joint, but it's not really locking up that joint. It's still allowing that joint to crack. It's still allowing that crack to form. But it is providing some restraint so that you maintain aggregate interlock across that crack face. So that's sort of the approach that ACI 360 for these lightly reinforced slabs utilizes. And if you look at 360, there's a nice table in 360 that goes through and looks at, for different percentages of reinforcing steel that we use, how much restrained shrinkage do we expect, and how much is the reduction in restrained shrinkage versus unrestrained shrinkage without using that reinforcement. And 360 basically points to using very low levels of reinforcing steel, 0.1%, to control that cracking, to allow that enhanced aggregate interlock to occur. So if you look at the sort of derivation of that table, all of the derivation of that really goes back to Park and Pauli back in 1975, looking at a very simple shrinkage model. So looking at uniform shrinkage of a symmetrically reinforced concrete element. So we have symmetrical section subjected to shrinkage. The shrinkage strain would be X amount, and by providing reinforcement, we're restraining that shrinkage strain back to a restrained shrinkage amount. And we're doing that by developing tension in the reinforcing steel and in the concrete. So the model that Park and Pauli uses is a little more complicated. It takes into effect creep strains, that type of thing. But the model is relatively simple. This is the model that's used to derive the concrete stress, the stress in the steel, and ultimately the restrained shrinkage strain. And in 360, there's some assumptions about what the shrinkage strain is, what the creep coefficient is, and then what the materials are. And if you plug all of those values into those equations, you end up with this table, which is identical to the one in 360. So this is basically the derivation of that table. Again, bear in mind that the shrinkage, the reinforcement ratio is recommended at 0.1%, so very low amount of reinforcing steel, to allow joint activation while maintaining aggregate interlock across that joint. So if you look at this model, and you're an FRP person, you say, oh, well, this is just mechanical properties at this point. So we can substitute the modulus of steel for the modulus of FRP. All of these are elastic equations. So we can go in and we can replace all of these material properties with GFRP material properties. And this is a table that we end up with. So now, because GFRP is less stiff, we can actually use a higher reinforcement ratio. And a lot of what Tony talked about earlier, I think is one of the things that we talk about when we look at GFRP and slabs on ground, is that because the material is less stiff, it is more compliant, it doesn't induce as much stress into the slab on ground, and this is really bearing that out. So we can use a higher level of, a higher percentage of reinforcement, but still maintain the similar reduced shrinkage strain and similar reduction in shrinkage strain that you would with low levels of steel reinforcement. So instead of the 0.1% we're now talking about 0.45% strain, or 0.45% reinforcement ratio with GFRP versus steel. So one other thing to think about with GFRP that's maybe a little bit different than steel, certainly different than steel, is the modulus. So when I showed this table, this is based on a ASTM standard bar. So an ASTM standard gives all the standard material properties for GFRP in D7957, and it says that the minimum modulus has to be 6,500 KSI. So in all these equations, we're using 6,500 as the modulus for the GFRP bar. Most manufacturers have modulus that's higher than that, depending on the bar that you look at. So modulus can be 6,500, but it can also be 8,500. So that's certainly going to affect what we do with this table. And now remember that we don't want to over-reinforce the slab, because now we're going to lock those joints up. So if we do have a higher modulus bar, we actually have to use lower percentage of reinforcing in that slab. So if we change this to 8,700 KSI, which is minimum in a newer ASTM standard that's out there, 8508, if we change that to 8,700 KSI, then we find that the percentage of reinforcement that we want to use is about 0.3%. Versus the 0.45 that we use with the lower modulus bars. So moral of the story, though, is that we want to be in that sort of range of 0.45 to 0.3% reinforcing steel in a slab-on-grade designed like this. So if you look at the manual that I showed earlier, the simplified pre-engineered manual, this is the table that you'll see in there for various slab thicknesses. You'll see these spacing requirements for different sized GFRP bars. And all of those spacing dimensions, if you work it out, this is about what their percentage works out to be. So right around that 0.3 to 0.4% reinforcement ratio that's used in those tables in that pre-engineered manual. Again, getting back to this idea that we want to provide enough reinforcement to maintain that aggregate interlock across that crack face, but not so much that we lock up the joint. Okay, so one other thing to think about with GFRP reinforcement and slabs on ground is this concept of the anisotropic nature of FRP. And I think the most important thing to think about with FRP and the sort of anisotropic behavior is not so much the strength or the shear strength of the bars perpendicular to the fibers, but it's to think about the coefficient of thermal expansion of the bars perpendicular to the fibers. So the coefficient of thermal expansion of GFRP bars is basically similar to steel and concrete in the long direction. In the perpendicular direction, it's several times higher, 2 to 3 times higher than concrete and steel in the perpendicular direction. So as thermal cycles are going on, you're getting a bar that's expanding quite a bit faster than the concrete around it. So what happens if the bar expands more than the concrete around it? It cracks the concrete. So we also have to pay attention to the fact that these bars do move differently in thermal cycles. So if you're using it in exterior environments in particular, ACI 440 recommends having sufficient cover around the bar to prevent cracking from occurring. And that sufficient cover is 1.5 inches or the lower of 1.5 inches or 2 bar diameters of cover to restrain the bar in thermal cycles to make sure that you're not cracking the concrete around the bar. So even though GFRP does not corrode, and we have all those benefits of it not corroding, so we don't need cover protection from a corrosion standpoint, we do need cover protection from the standpoint of restraining that thermal expansion of the bar itself. The other thing that we have to do, certainly when we're talking about, going back, when we're talking about this application is you obviously want the bar to be low enough that you're not going to cut it when you saw cut the joint. So you need to have sufficient cover to allow that saw cut to happen. And the thing that I would point out with GFRP to think about is that this may seem simple and easy to understand, but GFRP bars do have a tendency to float in fresh concrete. So they have a similar density to concrete. So they don't sink the way steel reinforcement does. They can actually float in freshly placed concrete. So from an application standpoint, you have to make sure that you're maintaining this cover and preventing that bar from floating to the surface. Otherwise, you will cut through the bar. So maintaining that top cover is certainly something to keep in mind when using GFRP reinforcement. All right. So with that, thanks again. Hopefully that gives you a little bit of insight to what we used in developing that simple manual, and also gives you some food for thought in terms of things that we have to consider when using coupling GFRP reinforcement with slabs on ground. So, thanks again.